just a quick review. In order to perform a position analysis or velocity or acceleration analysis, when you see a mechanism, first thing we do is okay, so we always start with position analysis first, and initially you will see a certain mechanism, and the first thing we do is to draw we call it vector loop or vector closure. And vector loop or vector closure means you need to draw some vector according to this mechanism, and this loop must be a closed loop. So for example, this one we draw R2 and R3 because we know the length of R2 and R3. So it will probably be a good choice for you. And then we draw another two. And here we use R1 and R4. And because if we define R1 and R4, we can use the information, the length of R1 to indicate the motion of the slider. The slider may move forward or backward. And if we move forward, then R1 will increase. If we move backward, R1 will decrease. So you can use R1 to indicate the motion of a slider. And for this mechanism, we probably use R2 as the input, the link 2 as the input, and the slider as output. So in this case, this R2 vector can be used to indicate the input, the angle of this R2. Yeah. Later on, in the calculation I wrote here, I use the theta 2 as the input. We'll see this later. Yeah, so R1 can indicate the motion of the slider. And R4 is, we won't use R4 to indicate anything, but it's necessary to form this closure loop, to form this closed loop. Yeah. So once you draw this vector loop, you can write a vector equation, and R1 plus R4 equals R2 plus R3. And last time, we've done this last time. And you can translate this vector equation into two scalar equations. So each vector equations, because vector equations including the x and y component, so you can separate them. So you can have two equations. One is regarding to cosine, one is regarding to sine. And right now, because this theta 1 is the angle of R1 and it's always horizontal, so theta 1 is 0. And theta 4 is the angle of R4. R4 is vertical, so it's always 90 degrees. So I just apply those theta 1 and theta 4 value into this equation, and it becomes like this. The cosine theta 1 is 1, so it just becomes R1 times 1. And cosine theta 4 is 0, so this 1 will disappear. So here it will become R1 equals R2 cosine theta 2 plus R3 cosine theta 3. Another equation, the second equation, the y component, because theta 1 is 0, so R1 sine theta 1 is going to be 0. And R4 sine theta 4 is going to be R4. So it becomes like this, the second equation on the board. And for this mechanism, because we use theta 2 as the input, so theta 2 is known, and this R2, R3, they are just the length of links, so they should be known. So R2, theta 2, R3, they are all known. Also, R4 is known because R4 is just a fixed length, an offset from this horizontal line to the center point of this slider. And no matter how it moves, this R4 is not going to move. And it's just a constant. You can measure this, the value of R4 once you get this mechanism. So anyway, R4 is also unknown, and R2, theta 2, R3 are known. So we found there are only two unknowns. R1 and theta 3 are unknowns for these two equations. So these two equations should be able to help us to determine the value of R1 and theta 3. Any questions so far? Okay, so you can just investigate these two equations, and you see because the second equation only has one unknown, so you can quickly use this equation to determine the value of theta 3. So you just rearrange this equation, and theta 3 should be arc sine of R4 minus R2 sine theta 2 over R3. So you can use your calculator to calculate the value of theta 3. And once you obtain theta 3, you can substitute theta 3 into the first equation, then you should be able to obtain R1. Any question for this one? So we'll see more examples later. And basically, once we see a mechanism, the first thing we draw a vector loop, then you should be able to determine two equations. Then you'll use these two equations to solve two unknowns. But sometimes you may have more unknowns in one mechanism. In that case, you will need more vector loops, but we'll see that later. And once we obtain this position information, we can further go with velocity analysis. So velocity analysis, we mentioned last time, basically if you have this position vector loop or vector equations, you do the time derivative for these equations, then you can obtain another equations. So it's basically doing a differentiation of each terms, then you will obtain the new equations. And this equation will include the information of a velocity. So you basically do time derivative of this equation, and you obtain these new equations. So basically, these velocity equations, you do the time derivative for each terms. So that's what we done last time, and this one is the same thing here. So you can simply just do a time derivative for these equations. R1, when you do a time, because theta 1 is a constant, so originally it should be R1. The first equation, original here is R1 cosine theta 1. And when you do the time derivative, because theta 1 is just a constant, so you become minus R1 cosine theta 1, sorry, positive, and minus R1 theta 1 dot sine theta 1. The original form for the time derivative of this one should be like this. But because right now theta 1 is a constant, so this term is just going to be 0. So only this one left. And cosine theta 1 is just 1. So that's why there's only R1 dot here. But R2 cosine theta 2 is a bit different. If you do the time derivative for this one, you'll get R2 dot cosine theta 2. originally you should get a form like this. But because R2 is a constant, it's just the length of the bar. And the length of the bar is not changing. So this term is 0. So you only have this one left. Yeah. So we only have this one left for R2. And R3 is similar to R2. So you only have this theta 3 dot term left. And same as the y component. And yeah, you do the same type derivative for this second equation, then you can obtain these equations. So to perform velocity analysis, you only need to deal with these two equations. And because all the information of those angle and this R2, theta 2, R3, theta 3, they should be known for now because we have done the position analysis. So we already obtained this theta 3, so you simply substitute the theta 3 you obtained from the position analysis into these two new equations. And so the value of theta, sine theta 3 and cosine theta 3 should be known. So the only unknown for these two equations are R1 dot and theta 3 dot. So which are the velocity, linear velocity and angular velocity. So we still have two equations and two unknowns. So these two equations should be able to solve these two unknowns. And here I think you can find the fourth equation. You can use the fourth equation to determine the value of theta 3 dot. And once you obtain theta 3 dot, you just substitute the value into the third equation and to obtain R1 dot. Any questions so far? And then we will go with the acceleration. So we haven't mentioned acceleration so far, but acceleration is similar to velocity. So you do the time derivative one more time. And here just some derivation of, suppose we have a vector r, and we do time derivative twice, then we should be able to get the acceleration information. So do it twice, eventually you should get these four terms. So we actually done this one before, if you still remember when we do the graphical analysis, and we say at most, and acceleration may have four components, including a sliding, Coriolis, a tangent, and normal. Yeah. So here is the same thing. We obtain these four terms. If both r and theta are differentiable, then you will get four terms. So this one is sliding, there's the tangent, and this one is normal or centripetal, and this one is a Coriolis. But sometimes because the theta might be a constant, if theta is constant, then these c and t terms will just be 0. Because they are time derivative for theta once or twice. But if theta is constant, these two will just be 0. If r is a constant, then this sliding will be 0 because it's doing the time derivative for r. If r is constant, this Coriolis is also going to be 0. Yeah. So it just depends on your case. These four terms may not always exist. Yeah. Depends on your vector, how the vector is defined. So anyway, so the same vector equation, you do the time derivative twice, then you'll get these new equations. So it's R1 double dot plus R4 double dot equals R2 double dot plus R3 double dot. So I'm going to write on the board. So this one is going to be long because there will be more terms here. And okay, I'll just write them on the board. So you can see there are just more terms for the acceleration. And for R1, well, the time derivative of R1 dot will be just R1 double dot. But for this R2 theta 2 dot sine theta 2, the first time you will do a time derivative for this theta 2 dot, so you will get R2 theta 2 double dot and times sine theta 2. But you also do the time derivative for the sine theta 2 again. So by doing so, you will get minus R2 theta 2 dot square and times cosine theta 2. And same as R3 theta 3. So this one is similar to R2 theta 2. And similar to the second equation, the y component equations. So eventually you'll get these two equations, and we got two unknowns. One is R1 double dot, another one is theta 3 double dot. And you can use the second equation, 6. You can use the 6 equations to obtain theta 3 dot. And then once you obtain the value of theta 3 double dot, you just substitute into the fifth equation to obtain R1 double dot. Any questions so far? Oh? And yeah, because for this case, well, it's either in this, so in these two cases, because R2 and theta R2 and R3, they are constant. So we won't have a Coriolis and sliding terms. So we only have a normal and tangent terms. But in some case, you may have 4 terms for the acceleration. So it's going to be more complicated. And this one is, well, it's not so bad. Any questions? And so far, even the position, in the position, velocity, acceleration, you'll find it's not so difficult to calculate them. But in some case, although you can still list 2 equations, but you'll find for some cases it's very difficult to solve them. And we'll introduce another case. And usually in that complicated case, we will use numerical method to solve the equations instead of using this. We call this analytical equations because we can write the closed form of the parameters of the unknowns. But in some cases, well, it's very hard for you to derive the closed form, the exact analytical solutions. So just take, any questions so far? And we'll move to another equations. So very common mechanism we've seen in this course is a 4-bar linkage. A 4-bar, I mean 4R, 4R joint. So basically it's R1, R2, R3, R4. And it's tilted with certain angle. So right now theta 1 is not 0, but it should be fine. It's not very special anyway. So for this mechanism, how are you going to draw the vector loop? So we need to draw a closed form. And also, so first, let's say if we want to use theta 2 as an input, and let's say we want to find the output theta 4. So we usually define the input and output, and we need to make sure when we define the vectors, the vector must include these 2 information in your equation. Otherwise, if you solve the equation and you still don't have the information, then you are just doing nothing. So just back to the previous slide. In the previous case, because usually if we say it's a crank slider, so we use a crank as a driver, and driving speed is theta 2 dot, or the acceleration is theta 2 double dot. And the output is the slider, the motion of slider. So it's either the velocity of the slider or the acceleration of a slider. And in the previous 6 equations, we can find, let's take a look at the velocity first. If I want to determine the velocity of a slider, so which vector or which unknowns indicate the velocity of a slider? Do we have any information of the velocity of slider here in these velocity equations? Any idea? Which unknown can indicate the velocity of a slider? Any idea? R1, yeah, R1 dot. R1 dot is the velocity. Thank you. I was waiting for someone. Okay. Okay, so R1 dot. R1 dot it's basically just the velocity of the slider. And R1 double dot is the acceleration of the slider. And we also have an information of input because the input is theta 2 dot. So we get an input, and by using these 2 equations, we can obtain the output. Yeah. So make sure your vector loop can give you those informations. Yeah. the equations should include the unknowns and the input. Okay, so back to this one. So, well, it's already shown. Okay, so theta 2 is the input and theta 4 is the output. So we need to make sure those vectors need to include the information of theta 2 and theta 4. So I think it's quite straightforward. You just follow all the links, all the 4 links, and just draw the vector. The direction of the vector is actually not so important. You can reverse them, and if you reverse them, you will just change the equation. You may move the terms from the right to the left, or to the left from the left to the right. But by my drawing here, because R2 is pointing to this direction, R3 pointing to this direction, and R4 is pointing from here to here, R4 pointing from here to here. So in this case, it's R1 plus R4 equals R2 plus R3. But you can always reverse them. It's not strict. If I change this R4 in this direction, then how should I change the equation? How should I modify the equation? Yeah, I just move R4 to the right-hand side. So it becomes R1 equals R2 plus R3 plus R4. Anyway. So direction is just upon your choice. Well, but you just make sure all the vectors can form a closed loop. So you can write the equation like this. So back to the original one. Okay, so once we obtain this vector equations, we should be able to find 2 scalar equations. So it's basically the x component of this equation and y component of this equation. So very similar to this one. And x component is the vector, the length times the cosine theta. And the y component is the length times the sine theta. So in this case, we have 2 equations, and we also only have 2 unknowns because all the lengths are known. So R1, R2, R3, R4, they are all fixed length. And if you see this mechanism, you simply measure the length of the links, then you can obtain the value of R1 to R4. And theta 1 is always a constant because it's not moving, it's fixed to the ground. So the value of theta 1 is just a constant value, and you can just measure it by on this graph, on this plot. And theta 2 is the input. So theta 2 is the input. So we only have 2 unknowns, theta 3 and theta 4. So by using these 2 equations, we should be able to find the 2 unknowns. The 2 unknowns, theta 3 and theta 4. But how do you think we can solve this one? Those unknowns are within cosine or sine. It's difficult to solve them. You can find the solution in the textbook. It's quite long, but it's specific for this mechanism. So I think it's quite time consuming to just to derive the analytical solution. But if you are interested in the analytical solution, you can refer to the textbook. But I'm not going to do it. But the main purpose for us to draw this vector loop is make sure you have these 2 equations. And if you remember, the title of this lecture is called Computational Analysis. So once you obtain these two equations, you can use a computer program to help you to solve these two unknowns by using these two equations. And we will briefly introduce how you can use it. We'll use MATLAB. Yeah, I will use a sample program, and you can just modify your equation and use that program to help you solve these two equations. But anyway, once you have these two equations, these two unknowns should be solvable. Yeah. So when you see a mechanism, the most important thing is you find a vector loop and you determine the equations. And you make sure the number of equations is the same as the number of unknowns. Then these unknowns should be solvable. So that's for the position analysis. Any questions so far? So how about the velocity analysis? So for velocity, you will do the time derivative for these terms. So let me write down the equation for velocity. And because R1 and theta 1 are both constant, so you can imagine once you do a time derivative, and those constants will just, R1 dot is going to be 0, and theta 1 dot is also going to be 0. So similar to the previous case, and you do the time derivative for these two equations, you can obtain these two new equations for the velocity. And for this case, the input is theta 2 dot, and we are trying to find theta 3 dot and theta 4 dot. So still you got these two equations to solve these two unknowns. But this one is actually easier than solving these two equations, because you see those unknowns, they are not within the sine or cosine. So once you put this value, you will just become like A theta 3 dot plus B theta 4 dot equals C. So once you apply those values, those position information into these two equations, you can rearrange these two equations in this form. And you'll basically just like A theta 3 dot plus B theta 4 dot equals a constant. And again, d theta 3 dot plus e theta 4 dot equals another constant. This type of equation is easy to solve, yeah, when compared with these two. Yeah. So actually, velocity is easier than position, yeah. But you still need to find the position information first. Yeah. But once you find the position information, it's easy for you to solve the velocity and also the acceleration. Because also for acceleration, you will just derive the equation first, but you also in this kind of form. The unknown won't be within the sine or cosine. Yeah. So it's basically linear equations. So it's easy to solve. Any questions? Okay, so just another example is still a 4-bar mechanism. But right now we got 1, 2, 3 R joint and 1 P joint. And let's say we still use link 2 as input. And we are trying to find theta 4. Three, 4. So let's say we are trying to find theta 4. And the input is theta 4 and theta 4 dot, theta 4 double dot. So position, velocity, and acceleration. So we should draw a vector loop which includes information of link 2, which is theta 2. We should write theta 2. Or theta 2 dot, theta 2 double dot. So I think this one is still quite straightforward. You can just follow the direction of those links, those lines. And so right now we form a closure loop, a vector loop or vector closure. So R1, R2, R3, R4. So you can write an equation. So based on the direction of my drawing, it's R1 plus R4 plus R3 equals R2. And we can obtain two scalar equations by these vector equations. And right now, one thing we need to make sure is we have two equations by using this vector loop. And we need to make sure the unknown, we only have two unknowns. So if we have only two unknowns among these four vectors, then the two equations, the x and y component equations, these two equations should help us to solve the two unknowns. So we need to make sure that, So right now, if we draw the vector loop in this form, we have four vectors, R1, R2, R3, and R4. And each vector includes the length and angle informations. So R1. So once you have these two equations, which I didn't wrote here, by the way, these two equations should include these 8 components, or these 8 variables. And we need to make sure among these 8 variables, there are only 2 unknowns. If there are only 2 unknowns, then these 2 equations can solve these 2 unknowns. So let's circle the nodes first and make sure we have only 2 unknowns. So let's start with the first vector for R1. R1 is a fixed link, so we know the length and the angle is not going to change. And we can simply measure R1 and theta 1 once we have this mechanism. Yeah. So these 2 are just fixed values and they are nodes. Yeah. You measure the angle here, it's always this angle, no matter how this mechanism is moving. So how about R2? R2 is just a fixed link. I mean, the length is fixed. It's a rich body. So R2 is a constant. So I circle it. And theta 2. Theta 2 is the input. It's varying by its input. We will assign a value for theta 2. So I put an underline. We know this one, but it's not a constant value. It's a variable. Yeah. But we know the value of this one because we assign the value for theta 2. And how about R3? R3 right now is indicate R3 is this vector starting from here pointing to this R joint. But because there's a sliding pair here, so if this one is sliding, then the length of R3 should change. And currently, we don't know how long it is. I mean, if I assign another theta 2 value and the length of R3 is going to change. And we will need to determine the value of R3. So it's going to be an unknown. We'll need to solve it. So R3 is an unknown. So I put in an arrow for the unknown. How about theta 3? The angle of theta 3 is also going to change. So theta 3 is also an unknown. Yeah. If you rotate this link tool, this R3 should change. Yeah. It should also be rotating. And right now we have no idea what's the value of R3. So the value of theta 3. So both theta 3 and R3 are variables. They are unknowns. And okay, so right now we have 2 unknowns. So we are hoping these 2 are the only unknowns. Otherwise, because we only have 2 equations, so these 2 equations should be able to only solve 2 unknowns. Let's take a look at R4. R4 should be a constant because it's pointing from this point to this point, and that's just a fixed length. Yeah. It's just a bar. It's a rich body, so R4 is a constant. How about theta 4? Theta 4 is changing, right? It's also rotating when you drive this mechanism. So it seems we got a problem. Right now we have only 2 equations, but we have 1, 2, 3. We got 3 unknowns. So if we want to solve 3 unknowns, how should we do? Right now we have only 2 equations, but it seems like we have 3 unknowns. And how can we solve these 3 unknowns by these 2 equations? So one solution is if we can find 1 more equations, and we got 3 equations, then the 3 equations should be able to solve these 3 unknowns. So we'll need to find equations which include those unknowns. And if we can find certain equations, they can determine the relationship between those unknowns. Then we should be able to use 3 equations to solve 3 unknowns. Any questions? Yeah. So by your observation, do you find any information here? Pay attention to theta 3 and theta 4. Yeah. Theta 4 and theta 3, this one is a fixed thing. It's a rich body. So the angle of theta 3 and the angle of theta 4 and theta 3 is a constant. Yeah. You bend a link into this shape. But if you rotate it, theta 4 is simply, or theta 3 is simply theta 4 plus something. And this something is a constant. Yeah. In this case, it looks like it's 90 degrees. So theta 3 is theta 4 plus 90 degrees. Yeah. Yeah, because these two vectors, they are perpendicular. And they'll be always perpendicular. Yeah. So this one is the third equation. So I'll rewrite it. Theta 3 is theta 4 plus 90. So we got three equations to solve three unknowns. Yeah. Or another, or you can simply substitute. Yeah. You just substitute theta 3 with theta 4. So you can eliminate this one. It's theta 3. Theta 3 is theta 4 plus 90. So right now we have enough equation to solve the same number of unknowns. So this should be solvable. Okay, so let's take a break first. Okay, so please be seated, and I'm going to say something about the final project. So if you still remember, you have a task to do, which is a final project. It weighs 25% for your total marks. I uploaded this instruction on Seba, so you can download it and to see it by yourself. By the way, so in this project, you'll be asked to analyze one or more mechanism. You have more time, you want to analyze more, then that's fine. But anyway, so choose one mechanism, and the mechanism can be an existing mechanism or a new mechanism invented by you. If you would like to, you see some mechanism is not working well, you want to improve the mechanism, then you can invent a mechanism by yourself. And yeah, so you can choose an existing mechanism or a mechanism invented by you. And you'll use a program, and I think next week or 2 weeks later, we will have a few lectures introducing how to use Inventor to perform kinematic analysis. But you are free to use other software like Creo. Creo is formerly called Pro-E. You probably heard Pro-E before. It can also perform kinematic analysis. Or SolidWorks can also do the work. So if you are not familiar with Inventor, you want to use other software, that's also fine, up to your choice. But since most of you have learned Inventor last semester, so I will introduce how to use Inventor to help you to assemble a mechanism and to perform some analysis. But if you haven't learned Inventor, you don't know any of them, I think it's very quick to learn it, because we won't ask you to draw something very fancy or very real. To perform the analysis, you only need to draw a bar. So 4-bar mechanism, you only need to draw 4 bars. And you draw 4 bars, you spend 3 seconds, you can draw a bar. Yeah. You don't need to modify the bar and with a very fancy shape. You just draw a rectangular bar, then you can perform the analysis. So I think a drawing part won't be a big problem. And next week, I'll go to book a computer center and for our lecture. But once I book it, I'll post online, and you will take the lecture in the computer center. And so just pay attention to the announcement. Probably next Wednesday, yeah. But because I haven't booked the computer center, so just wait for the announcement. Yeah. So you can use any software, Inventor or Creo, or if you like to use MATLAB to do some coding, that's also fine, or Python. Just up to your choice. So you choose a mechanism and to perform kinematic analysis. And the analysis may include position, velocity, or acceleration. That depends on your case. For some cases, it's important to perform position analysis, but it may not be so important to perform velocity analysis. And the key point is you need to find the important factor or important variable for your mechanism. The thing you want to analyze must be meaningful. You don't just randomly analyze the position, velocity, and acceleration and just put everything on the report. You must make sure those variables, those unknowns you analyze are useful, are meaningful. Yeah, don't just put some value there, because if you just put some value, well, people won't understand what you are analyzing. Yeah. So try to find some important factors that influence the mechanism, and that's important for the mechanism. Yeah. So, so for this project, it's a group project. So 3 people per group. So try to find your partner during these weeks and weigh 25%. And the project will include an oral presentation and a final report. And for this should be final report. The final report will weigh 70%. So you should write the report no more than 15 pages. Yeah, and you can write it either English or Chinese. That's fine to me. Yeah, and there are some percentage for how I will evaluate your report. So I'll focus more on how you analysis and how you use this mechanism for certain applications. So you'll find a mechanism that fit certain applications. Yeah. Then you will, based on that applications, to define what variable you are going to analyze in your project. Yeah. And also the format will also weigh 15%, and how you organize your article, your report will also weigh 15%. And there will be 30% for the oral presentation. And because I think we'll have more than 20 groups, so the presentation time will be very short because we don't have so many time. Yeah. And so try to control your presentation within 5 to 6 minutes. I think it's going to be very short presentation. So for the presentation, focus on, it's more like you are marketing your mechanism. So don't spend too much time on how you analyze the mechanism. You can mention a little bit, but not spend too much time. Because, within 5 or 6 minutes, if you want the audience to understand your principle, I think it's very difficult. Yeah. So focus on how this mechanism is going to work, what's the application. I think that's more important for your oral presentation. Yeah. And for this presentation, I wait 25% for time control. Time control means if you finish within this time, you will get 4 marks for this 25%. Yeah. Basically, I just want to control you. Just do your presentation within the required time. And also how you present and the content in your slides will weight 75%. So here are some important dates. And so the first one is temporary because I haven't booked the computer center. But let's say we'll probably do the lecture for Inventor for kinematic analysis next week. If it's not next week, then it will be the week after, the week after. On Wednesday. Wednesday is longer. Okay. And on November 28th, try to submit your proposal. Your proposal is how you are going to, which mechanism you are going to analyze, and like what variable you are going to analyze, and what application you can use this mechanism for. Try to write those things. It's going to be a very brief proposal, 50 to 100 words. And the purpose for this proposal is for me to review if your project is achievable. Yeah, you may have a very good topic, but you may need to spend like 1 or 2 years to finish the project. Then I would say that's too difficult. Yeah. I just need to make sure your project is not too easy or not too difficult. Yeah. So try to submit this proposal by this time. Then you'll have more time to work on your proposal, work on your project in the right direction. Yeah. So submit a proposal and including your group list. So group list means who is in the group. And so was approximately have 1 or 5 weeks for you to work on this project after you submit this proposal. Well, but you can actually already start it from now. Yeah. But anyway, so on December 26th and January 2nd, we will have the oral presentation. And the same on, sorry, I didn't change this one. It's January 2nd, you will submit your final report. Pardon me? Yeah. You can submit a hard copy to me, or you can just send an email. If you don't want to print it out, you can submit your electric version to me, soft copy to me. And there are some reference here. One is the inventor. You know you can download inventor for free. It's legal, it's not illegal. I'm not talking about illegal. If you are a student, you can register an account and inventor. Autodesk provides a free version for students. It's a complete version, it's not a light version. Yeah, so you can do everything with the student version. Yeah. So, or if you don't want to install it in your own computer, you can just go to a computer center, the Mechanical Engineering Computer Center. It's on the 6th floor of the engineering building. Yeah. And there's another reference I put here. I think he's a retired engineer, and he finished like 2,007, more than 2,700 mechanisms online and in Inventor. He drew everything and performed the analysis in Inventor. So it's one example. So he drew 2,700, more than 2,700 examples. So I think if you have no idea what you are going to analyze in your project, you can just go to browse his YouTube channel. Yeah, and I think this can inspire you. Yeah. He has many examples done in inventors. Yeah. Yeah. So, any questions? I have some report from the past few years. So if you are interested in how other people have done in this project, and there are some reference here. Any questions? Yeah. So try to find your partners, and yeah, you can try to do some brainstorming and to come up with some ideas. Okay, any questions? Okay, so let's back to this computational analysis. So you can find in computational analysis, but although in the previous slides, it may also have the tangent, normal, Coriolis, or sliding components, but actually we don't focus on those terms too much. You just write down all these equations and try to solve these equations, then you can find the output or find the unknowns. So it's more mathematical. Yeah. It's not like in graphical analysis, you need to make sure you know the direction of those components. But in this computational analysis, well, as long as you can write down those equations, then you will be able to solve them. You don't necessarily need to know their directions because, well, yeah. So let's take another example. So another 4-bar linkage, and let's take a look of this left one. So we are trying to find the motion including the position, velocity, acceleration. But anyway, if we want to find the motion of this point P, we'll need to define a vector loop first. Determine a vector loop first. This one is a bit more complicated. Yeah. So how should we draw the vector loop? Actually, there are more than one way you can do this one, but let me show you my solution first. But this one is not the only solution, but yeah. Anyway, it can. This one can help us to solve to find the motion of point P. So we still use a link to this one, this bar as an input, but this one because the shape is a bit complicated, so I use more vectors to complete the vector loop. I still follow the direction of these links, so I still have R2, R3. Those are just following the original links. And also R5 indicate the length here, R7 indicate the length here, and I have another two, R6 and R4. R4 is along the sliding direction. Yeah. When we draw this vector, I think one important factor is we always have a vector that's pointing to the direction that's along the sliding. So remember also in the previous examples, in the crank slider, we also have a vector that's following the sliding direction. In this one, we use R1 to indicate the sliding direction, or this R1 eventually can help us to determine the sliding velocity of this slider. So in this case, we still use the same trick, the same skill. We determine an R4, which is the sliding direction of this slider. Right now, there are two sliders. There's another slider here. So we also have another R3. That's the sliding direction of this sliding pair. Yeah. So the input is linked to, and the output is the motion of P. So a very first thing we need to do, we need to make sure this vector loop can have the information of the motion of P. And if I draw it in this way, then which variable can indicate the motion of P? How do you think? The motion of P. I'm saying R4 is going to be indicating the motion of P. Because this one may slide here later. This link 4 is sliding up or down. And when it slides, this R4 is going to change. The length of R4 is going to change. And you can see the P is going to move up. If this slider moves up, P is moving up, of course. Yeah. And basically, the motion of P is the same as the motion here. So this R4 will be able to help us to determine the motion of this point. And the input is R2, the input is theta 2, is the angle of the link 2. So we also have a vector, which is R2, that can help us to put the information of the input within this vector loop. So it seems this vector loop should work fine because we have an information of input and also have an information of output. The motion of P will just be the length of R4 or the velocity of R4. Any questions so far? Any question for this one? So I'll just erase it. So once we have this vector loop, we can just write the equation. So R2 plus R3 plus R5 plus R7 equals R6 plus R4. And because although we have so many vectors now, but we have only one equation. So we have only one vector equations. And this equation can generate two scalar equations. So we need to make sure among these two equations, there are only two unknowns. Otherwise, this won't help us to solve the unknowns. If we have more than two unknowns, then we will need more equations. So let's see if we have only two unknowns or if we have more. So let me list all the R2, R3, R5, R7, R6, R4, theta 2, theta 3. So let's see if we have only two unknowns. Yeah. So how about R2? Is R2 an known or an unknown? R2 is just a fixed link. It's a rigid body. So R2, the length, here I mean is the length. The length is fixed, and you can simply measure it, and it's not going to change. So R2 is known. Theta 2 is input, so it's also known as the input, it's assigned. R3 is an unknown because the slider may slide. If we slide and the length of R3 is going to change, it can go up or it can go down. So this one is an unknown. For unknown, I put an underline. How about theta 3? theta 3 is rotating as well, but it's similar to the case we discussed previously. Theta 3 is just perpendicular to theta 2. So I should say R3 is perpendicular to R2. So theta 3 and theta 2, the difference between theta 3 and theta 2 is they are forming a constant angle. So theta 3 is theta 2 plus 90 degrees. So you can consider theta 2 and theta 3, they are the same unknown. So they consider. So, but because theta 2 is known, so theta 3 should be known. So I will also put arrow means input. And underline means unknown for now. How about R5? R5 is also, the length is also fixed. Yeah, it's not going to change it. So R5 is fixed. Any questions so far? No? Okay. How about theta 5? Is it a known or unknown? Theta 5, yeah. Theta 5 and theta 3, the difference between theta 5 and theta 3 is always a constant. And actually, this R5 is the same direction as R2. So theta 5 is the same as theta 2. So this one is still known. So far we only have one unknown, R3. So it seems it's working well. How about R7? It's also unknown. It's similar to R5. The length is not going to change. And how about theta 7? Yeah, it's fixed. And you need to measure it, but it's perpendicular to this ground. It's certain angle, but it's fixed, it's known. It's a constant. So it seems it's working fine. So far we only have R3 as the unknown. And how about R6? R6 is pointing from ground to ground. So this one should be fixed. I define this one. But I define this one as from this ground point to another ground point. Yeah. This one is defined by me, and I say it's constant. I'm not going to change it when this linkage is operating. It's constant. And how about R4? R4 is going to change, as we mentioned previously. R4, if you do a slider move up, this R4 is going to be extend. So R4 is unknown. And theta 4 is constant because it's just along the ground. Yeah. So although originally we have so many variables, but when we investigate them, we found only R3 and R4 are unknowns. So by using this vector loop, we can generate two equations, and these two equations should be able to solve these two unknowns. Yeah. Three depends on if you see this one as the equation, then we have three. Pardon me? Yeah. Yeah, so only R3 and R4 are the unknowns we are trying to solve. R3, you can simply obtain R3 once you know the input. And we know the input for sure because there's assigned by us. And also theta 5 is the same as theta 2. Any question for this one? And this one is working fine. Yeah, I think it's working fine because we can solve it. But in the textbook, it introduced another trick. We actually don't need to use so many vectors, and we can still find the velocity of point P, or the motion of point P, instead of setting too many, so many vectors. Yeah. So let me pop out. Save. So right now we have this vector loop. And sorry, let me go back. I'll write this on the board first. So right now I have this R2 plus R3 plus R5 plus R7 equals R6 plus R4. Right now I write in this way because I'm following my order. R3 is after R2, R5 is after R3, so I write in this way. But we can always rearrange them, right? I can change the order. I can R5, R3. It should be fine because if that equation is valid, this equation should also be valid. It doesn't matter if I change the order of them, right? As long as they are on the same side. Yeah, it shouldn't be a problem. So here what I'm going to do is I'm going to change the order of them. So I only move the So what I'm going to do is I'm going to change the order. So originally it starts with R2 and goes with R3 and R5, R7. Right now I'm changing the order of R5 and R3. So if the previous vector loop is valid, this vector loop should also be valid. I only changed their order, but they should be the same as the original vectors. But right now, if I change in this way, I actually can combine R2 and R5 together to become a new one. So yeah, so just keep this in mind. Yeah. So right now I can combine R2 and R5. Let's say, let me call it R2 prime. It's R2 plus R5. And also, if you take a look at R7 and R6, because R7 is a fixed value, the length of R7 is fixed. Also, R6 is fixed. And right now, I determine the R6 is in the same direction of R7. So I'm going to do another thing is I will subtract these two equations by R7 on both sides. Use another color. So I subtract the R7 on both sides for these equations. So, and also combine this R5 and R2 and R5 together as R2 prime. So I can rewrite this equation in this form. So what does it mean if I subtract R7? How this vector is going to change? If I subtract R7, then R7 will disappear. So it's like this. So I modify this equation, and according to this modified equation, I also modify my vector loop. So I just remove R7, and the other side, original R6, I replace with R6 prime. And the R6 prime means R6 minus R7. So I make this R6 subtract this R7. So right now it's forming another vector loop. The new loop is this one. So I actually can form a simpler loop. This loop has only 4 vectors. Which is R2 prime and R3. R3 is the original R3. Also R6 prime. R6 prime is, I shorten the original R6 by subtract R7. Yeah. And also R4. R4 is the original R4. Yeah. So if this one is working, this one should also work. Yeah. So actually, instead of using 6 vectors, you can use only 4 vectors and to analyze the same mechanism. So this mechanism is actually working the same as this mechanism. The difference between them is we shift the, let me erase, oh. The difference between these 2 mechanisms is we simply shift the sliding track to the point P. Originally, the sliding track is here, but right now we shift the track and let the track pass point P. Also, we shift this track, this original sliding track, and let it pass point P. But these 2 mechanisms, they should be equivalent. according to our equation here. The very first equation is for the original vector loop we draw. But somehow we can modify the original vector loop into this way. Yeah. And when you compare these two mechanisms, you will find you can draw exact the same vector loop in this second mechanism. Yeah. And by doing so, you can make your vector loop simpler because right now you have fewer terms. So this one is a way for you to reduce the vectors, but actually you can use the original one. If this original one for you, you can just stay with this one. But if you prefer to use fewer vectors, well, you can go with this one. Any questions? Yes?
Are there any limitations of using the second one?
I would say no. Yeah, yeah. I think because what we do is we combine these two, but the only difference between these two is right now we have no information of R2 and R5 alone. We combine them together. But actually R2 alone and R5 alone doesn't mean anything. I think it's not quite meaningful. Yeah. Another one is R6 minus R7, but it's also, because I define R6 by myself, and it doesn't mean anything useful. Any question for this one? Okay, so just a few more examples, and it's already shown here. All right, so there's also a 4-bar linkage. Right now there's an R joint, and 2 sliding joint. It's also 4-bar. And right now, let's say we wanna the input is theta 2, and output is the sliding. So output is the V, let's say is motion of B. Motion of B. B is just right at this R joint. So if we want to draw a vector loop, we need to make sure those vectors, including these two informations. You need to include the angle of link 2, because this one is the input. Also, we need to have information of the output. So I just draw this triangle, and R2 is to indicate the information of link 2. And R1 is just something for vertical. And right now for this case, R4 can be used to indicate the motion of point B. So this vector loop should work well for this required problem, required motion of B. So we just need to make sure. So right now we have R1 plus R4 equals R2. So we have one vector loop, so we will have two equations. So another thing we need to confirm is we need to make sure there are only two unknowns. So we list all the variables, R1, R2, R4. Theta 1, theta 2, theta 4. So let's see how many unknowns within these 6 variables. So how about R1, the length of this R1 vector is known, right? Now, it's not going to change because it's only indicate the distance from this adjoint to this track. Yeah, it's not going to change. It's constant. Theta 1 is also constant because I defined it in this way. It must stay vertical. And R2 is, how about R2? If you rotate this bar, R2 is going to change. The length is going to change. Yeah. And right now we say the input is theta 2, so R2 is unknown. Theta 2 is known, is input. And R2 is unknown. I put the underline. So it's unknown, and theta 2 is the input, so this is known. And R4 is an unknown because obviously if you rotate this link, and the length of R4 is going to change because the slider is going to slide in forward or backward. So R4 is an unknown, but theta 4 is constant. It's always stay horizontal. So we got use this vector loop to obtain 2 equations, and these 2 equations to solve these 2 unknown, R2 and R4. Any questions? Okay, let's see. Okay, last example. So still a 4-bar mechanism, but just different combination. Yeah, so 2R joint and 2P joint. So let's say input is link 2, theta 2, or omega 2 or alpha 2. Output is the sliding velocity of 4. Let's say it's V4. Motion of 4. So to determine, so we need to make sure our vector loop can include these 2 informations, include the orientation of link 2 and also the motion of link 4. So you can think of it, think about it. Yeah. Anyway, I determine in this way. It's also a simple vector loop. It's just triangle. So R2, you can use R2 included information of theta 2, and R3, R1. I can use R1 to indicate the motion of link 4. Yeah. And R1 is parallel, so this vector is parallel to this track. Yeah. These 2, they are parallel. So in this case, R1 can indicate the motion of link 4. So we write down the equation and we see if the number of unknown is the same as the number of the equations. So we got 1 vector loop, so we got 2 equations. And right now we got R1, R2, R3, theta 1, theta 2, and theta 3. R1 is R1 an unknown or unknown? Well, it's unknown because, yeah, it's unknown. It's determine the motion of 4, and that's what we are trying to determine. And theta 1, how about theta 1? Yeah, it's a constant. And the theta 1 is parallel to this ground. And the ground is fixed, so it should be a constant and it should be a known. How about R2? R2 should be constant, right? Because it's between two arc joint. It's not, the density is not changing. So R2 is a rich body. Theta 2 is the input. How about R3? R3 is changing, right? Yeah, because the slider is moving up or down, then R3 is going to change. But how about theta 3? Theta 3 is a constant. It forms a certain angle with the track. Yeah. Yeah. It's a rich body, so its angle is this angle, let's say alpha. Alpha is fixed. So and theta 3 is also fixed. So fixed. So only R1 and R3 are unknowns. So we got two equations. We should be able to solve these two unknowns. Okay, any questions? So we'll continue to work on this next Monday, and probably we'll go to the computer center next Wednesday. I'll just post an announcement and just pay attention to that. Okay, so that's it. See you next week.